Fubini's theorem basically says that the double iterated integral is equal to a corresponding double integral of the type we studied in the last section. So let's let f be continuous on some sort of rectangle. So the rectangle, we'll call it the rectangle from created by the interval from a to b on the x-axis and from c to d on the y-axis. So f is continuous on that. Then, let me make some room here. Here's the conclusion. This is the big conclusion. The double integral of the type that we studied in the last section over R of f of x, y, dA is going to be equal to the integral of the integral. Okay, the integral, if it depends on what order we want to go with. If we go with a differential order of, say, dy dx, then it will be the integral from a to b of the integral from c to d f of x, y, dy dx. We're saying that the double integral is equal to this double iterated integral, where a and b and c and d come from the subintervals, or the intervals rather, on the x and y axes that create the rectangle that we're integrating over. But you could just as easily flip it around and make it the integral from c to d of the integral from a to b of f of x, y, and then it would be dx dy would be the differential order there. It'll make more sense when we look at examples, but let me try and help you believe this. This would not be a formal proof or anything close to it. But let's say that here's your c to d. So the xy plane, here's the y-axis, here's x. Here's your c to d on the y-axis and your a to b on the x-axis. So you see the rectangle we're talking about, I'm outlining it right now. So suppose we're integrating a function over that rectangle, and for the sake of argument, suppose that function is positive right now. It makes believing this a little easier. Suppose you just have a little strip of that function. Here's our little strip of the function. It actually goes out, and maybe it hovers over the entire rectangle and beyond. But I'm just showing you this little strip of the function f of x, y. You guys see the strip that might represent z equals f of x, y? Okay. And in fact, think of this slice that I'm taking between the region R in the xy plane and the top, this wavy top function. So if you look at this entire slice, eventually I'm going to be talking about the volume of this entire slice. Okay? Now focus in on this representative column, much like the type we talked about in the last section. Can we come up with, say, the area of that shaded region right there? What would be the width of this rectangle, this vertical rectangle in space right here? What would be the width? It would be this, right? Delta y, do you believe that? And what could we use to estimate the height? I didn't pick a sample point, so we'll just say for some xy in here, then the height would be f of xy. Would you believe that? Yeah? So the area then, that area of that rectangle, I'll just use a drawing here. The area would be what? Well, height times width, right? F of xy delta y. Would you believe that? Okay. What would be the area of this entire slice? of that region between F and the XY plane that I've highlighted kind of in red there. So what would be the area then, or what would represent the area of slice? Where that thing that I've tried to highlight with the lines there is the slice. Well, you'd have to take a lot of these rectangles and add them together, right? A lot of these rectangles and add them together, wouldn't you? And that would be, we would represent that with an integral, right? We kind of think of an integral as a sum, even though it's a limit of a sum, right? So think in terms of an integral being a sum, even though in the back of your mind think it's not quite a sum, it's a limit of a sum, not quite the same thing. So the area of the slice could be represented by the integral from C to D of f of x, y, dy. You believe that? Yeah? Now, okay, so if you think of then the volume of the slice with the thickness delta x added onto it, right? So this thickness, which is represented by delta x, so I suppose that's a slice too, but it's a slice that has some depth to it. What would the volume of just this one slice be? Volume of the slice with depth delta x. What would that be? Well, it would be this, right? Because that's the area of the side slice, right? The side of the slice times delta x, wouldn't it? So that would be, let's make sure this is in the video. The volume of the slice with depth delta x then would be this, the area times delta x, right? So that whole thing, delta x. And now imagine summing all such slices, where the slices become skinnier and skinnier, right? And the number of slices goes to infinity. Then wouldn't that represent the volume underneath the entire function and above the region in the xy plane? Okay, so then the volume of that region, or between the region R and F, would be the integral from then A to B of the volume of all such slices. So that would be, okay, so what would that look like? So this would change to a dx. So we would get the integral of the integral from C to D, f of x, y, dy, and then dx. Okay? And so that is exactly, in the last section, what we called the double integral over R of f of x, y, dA. And it works when f is not positive, so it doesn't have to represent volume. But it's a convincing argument when f is positive. Okay, that's what Fubini's theorem says. And there's no reason why you can't switch it around, switch the slices around to get the other result as well.
Let's find the volume of the solid bounded by the cylinder x squared plus z squared equals 9 and the plane x equals 3y in the first octant. Okay, to get an idea what the solid looks like, we better first draw this cylinder. So here we go. Let's suppose this is the z-axis. This is positive z-axis, positive x-axis, and positive y-axis. Okay, in the first octant, the generating curve for this cylinder is a quarter circle of radius 3. So let's go out 3 units on the x, on the z and the x. and draw that quarter circle. It's a little too flat. Let's try that again. Okay, third time's a charm. Better, better, nope. Okay. Take two. Okay, take two. Okay, let's find the volume of the solid bounded by the cylinder x squared plus z squared equals 9 and the plane x equals 3y in the first octant. If you want to find the volume of the solid, we've got to draw it. So let's start with the cylinder. It's actually just a quarter of a cylinder in the first octant. So let's draw the first octant. There is the positive z-axis. I'm going to make the positive x-axis go like so, and I'll make the positive y-axis go like so. Now, x squared plus z squared equals 9 is the tin can shaped cylinder. The central axis of it is the y-axis, and its generating curve in the first octant, it'll actually be a quarter cylinder. So its generating curve will be the quarter circle of x squared plus z squared equals 9 in the first octant. So let's draw that. It's got a radius of 3. So let's go up 1, 2, 3 on the z, out 1, 2, 3 on the x. Draw the quarter circle like so. And then this is the generating curve, and if you translate it parallel with the y-axis, you'll get the quarter cylinder. So it'll come out here somewhere. Draw another copy of the generating curve like so. And just to give it some depth, I'll draw this corner back here. So there's your picture of your cylinder. We're not done yet. We still need to draw x equals 3y. Well, if you think about it, x equals 3y goes through 0, 0 in the xy plane, goes through 0, 0. And it also goes through 3, 1, right? If you plug in 1 for y, you get 3 for x. So let's suppose, for the sake of argument, let's stretch out our scaling here and say that this value right here is 1. Then 3, 1 would be right here. And in the xy plane, x equals 3y then is the line given by this line segment in green. At least it's part of it anyway. And then if you think about it, if you translate it parallel with the z-axis, you're going to get a wall that will intersect the cylinder. Well, it's got to intersect it in something, some kind of curve that looks like this, that goes down because it's got to lie inside that cylinder. So we get this kind of wedge shape here. That's bounded by the xy plane, the xz plane, the cylinder itself, and of course x equals 3y in space. And that wedge shape is what we're looking to find the volume of. Now you're integrating over this region here. Whoops, I meant to change colors there. This region here in the xy plane. That's the region above this triangle in pink formed by the x-axis, the line in the xy plane, x equals 3y, and this line x equals 3, this would be a line x equals 3 in the xy plane. that's the region you're integrating over. That's like your floor. And then the wedge shape here, whoops, the wedge shape and the cylinder from that wedge shape is your roof. So we're going to integrate over that region. Okay, so how is that region created? Well, like I said, if you look at the line x equals 3y, which goes through 0, 0, and 3, 1, then this is the region here that we're integrating over. Okay. So you can experiment a little bit, but I think we're going to need to use vertical rectangles here as representative rectangles to help us get our limits of integration. You can try it with horizontal rectangles, which would correspond to the differential order dx dy, but I think you'll run into trouble if you do that. Okay, so the bottom of this rectangle is given by just a height of 0, y equals 0. The top of this rectangle is given by x equals 3y, but if for vertical rectangles you're going to want y as a function of x, so y equals 1/3 x or x over 3. So when we go to set up our double integral, we're going to use that. We'll say that the volume is the double integral. Okay, remember the roof is just given by the cylinder. It's the cylinder turned into this wedge shape over here, but it's just a cylinder. Oh, we better solve that for, can you see what I'm doing here? We better solve that for z in terms of x. Let me do it down here. Z is going to equal, let's say it's the top part, so the positive square root of 9 minus x squared. That's what gives you the roof here. We need z as a function of x and or y. And so that will be our integrand. And remember, we're going with the differential order dy dx. Okay. To get the inner limits of integration, look at the bottom of the rectangle, look at the top of the rectangle. 0 to x over 3, or 1/3 x, I'm going to call it. And then, of course, x runs from 0 to 3. So now you'll see why I set it up with this order of integration, because I want to integrate with respect to y first. It would be difficult to integrate the square root of 9 minus x squared with respect to x. But if I integrate with respect to y first, things are going to work out real nice. Take a look. So if I integrate with respect to y, I just get, well, y times the square root of 9 minus x squared for the inner integral, the inner antiderivative, evaluated from 0 to 1/3 x. Okay, so how am I going to write that? Well, I'll just put the y in the evaluation brackets. And I'll leave the square root of 9 minus x squared outside that. The outer integral hasn't gone anywhere. And then you can see I'm just going to get 1/3 x here when I plug in the upper limit of integration minus 0, which doesn't do a whole lot. Okay, so I'm going to bring the 1/3 out front. Integral 0 to 3 square root 9 minus x squared, and I have just x left in here, dx. And it's a simple u substitution with u equal to 9 minus x squared, and that makes du equal to negative 2x dx. So all I need is a negative 2 in here, and I have a perfect du, but I need to compensate by multiplying out here by negative 1/2. So now I can think of this as just this in here, this radical is u to the 1/2 power. So now, okay, this will be negative 1/6 out front. Integrate u to the 1/2. Well, okay, remember u is 9 minus x squared. I'm not actually making the substitution here. That becomes 9 minus x squared u to the 3/2 times 2/3. And then we're evaluating that from 0 to 3. Evaluation brackets don't include the factor of 2/3. There's no reason for that. We'll evaluate it like so. Now, okay, out front here, what do we have? We've got 1 and 3 there, so that gives us -1/9 right there. Plug in 3 in for x here. Plug in the upper value here, the upper limit, and you just get 9 minus 9 to the 3/2, that's 0. Minus, plug in 0 here, you get 9 to the 3/2. And that's a minus right there, right? Okay, so that means we have positive 9 to the 3/2 over 9 is our answer. But if you can evaluate this. The square root of 9 is 3, cubed is 27. 27 over 9 is 3. So it's 3 cubic units, whatever the units are, 3 cubic units, that's your answer.